So right now it will be very elementary. And then in the second talk, I will explain why I'm interested in this elementary geometry. So let me start with the notation. So I will consider projective variety, and I always use the classical notation. These are lines in vector space. So projective variety. And usually irreducible. And then the notation is denoted by z hat, the cone over z inside the vector space. And when you choose a point in z hat, I write regular, meaning a regular point, a smooth point of this cone. Then we have the tangent space, the tangent space of the cone at that point, and this is a subspace of the vector space. Okay. Now let me just motivate my later definitions. Let me define this. It's something completely trivial. Annihilator of z. Annihilator of z just means that these are linear functionals such that lambda alpha equals 0 for all alpha. So linear functionals which vanishes on this variety. And then, of course, if you look at annihilator of PV, when Z is the whole space, this is 0. These are all trivial. And then we have the notion of linear non-degeneracy. So Z is definition, which everybody knows, I guess. Z is linearly non-degenerate. If annihilator of Z is the same as annihilator of PV. If it's 0, then it's. So it means that it's not, Z is not contained in any hyperplane. Okay, so why do I write it in this stupid way? Because I try to motivate next definition. Now I will define the following. I don't know whether there's any standard notation, so I will use sigma z. Sigma z is now two forms such that theta alpha beta is 0 if alpha is in z hat, regular, and beta is. So these are two forms which vanishes on tangent vectors to the variety. And then it's easy to see that sigma PV is 0. Because sigma PV just means that two forms which vanishes for all choice of alpha and beta. So it's 0. Then Z is tangentially non-degenerate if sigma z is equal to sigma PV. It's sort of similar to this here. Instead of linear non-degeneracy, we define, this is the definition. Okay, and what's behind the, geometrically, what's behind this is
at regular points over. At regular points.
Regular, only at regular points. Yeah, yeah. Okay. And then the geometry behind this is, of course, if you look at tangent lines, this is a variety of the Grassmannian of lines inside the vector space. And tangent lines, this is defined as the linear combinations, the exterior combination of so this is a collection of tangent lines to the variety, lines tangent to the variety, and you take the closure of this thing. That's exactly the variety of tangent lines inside the Grassmannian. Okay. And then if G is tangentially non-degenerate, means that this is linearly non-degenerate. Let me write it this way. Means that these tangent lines is linearly non-degenerate. So in other words, tangentially non-degenerate means that the tangent vectors to Z span all two vectors of the vector space. That's the definition. I think up to here is reasonably classical. So there may be more standard terminology. But this is the term I just picked by myself. Now I will go one step further. Sigma prime. This is now here we took all two forms, but here we take all homomorphism from square of V to V itself, and such that sigma alpha beta is in the span of alpha and beta. If alpha is regular and beta is so I define this notion, and then let's see what happens to sigma prime PV. Here sigma PV was 0. Now sigma prime PV is such that sigma alpha beta for all alpha beta that's sigma prime PV. Okay. Now let's define a homomorphism from hom VC to, I write it J. Here to here in the following way. If you are given a linear functional on the vector space, I'll send it to the following element here, defined as lambda alpha beta minus lambda beta alpha. Okay? That's an element here. So you can, yeah. And you can see that this is injective. And you can check that these are actually exactly this. So images, image of J is sigma prime PV. that you can check. It's an exercise you can check. So, in other words, sigma prime PV is actually isomorphic to the dual of V. This is okay. Now I make the following definition. This also I don't have any standard terminology, so let me just, for today's sake, let's call that G is strongly tangentially non-degenerate if sigma prime Z is equal to sigma prime PV. By the way, note that this is always contained in here. Sigma prime PV is always contained here. I mean, it's kind of relation that this is always contained in here and this is always contained in here. So by that, because of the definition, so there's always inclusion in one direction. And if this is equal, then I will say it's strongly tangentially non-degenerate. Now this is an easy exercise that if Z is tangentially non-degenerate, then it is linearly non-degenerate. And this is very easy. Now I also very easy, but let me state it because it's something new to you, that if Z is strongly tangentially non-degenerate, then it is tangentially non-degenerate. So that justifies the terminology that this is strongly tangentially. And let's see why this is. This is so if so let's give a proof as a illustration of this idea that if G is tangentially degenerate, so I will define, I assume it's not true, then let's prove that this is not true. So if G is tangentially degenerate, now what does it mean? It means that there's some element here which is not non-zero element here. So it means that there exists some two form here, two form on V, such that theta alpha T alpha G is 0 for all alpha regular. Okay, that's the definition. Now this happens, then fix W. Okay. Let me say something here. That one thing I forgot here. That here you have to assume the dimension of V is at least 2, but it's sort of. I mean, in our situation, we always have higher dimension. Anyway, so fix a point in W, and then we define for all alpha beta, sigma alpha beta equals theta. So let's define sigma. this way, just a multiple of a fixed W by this constant, theta, alpha, beta. Then it's trivially that this sigma is in sigma prime of Z, because this is 0. It's always 0. So, so because sigma alpha beta is 0 if alpha is in G hat regular and beta is in T. So this is G inside the sigma prime G, and this is certainly not inside sigma prime PV, because sigma prime PV is always of this form. It's rank 2, at least rank 2 for every element, but this is rank 1. So this cannot be. So this implies that so sigma prime G is different from sigma prime PV. So this proves this, that if G is strongly tangentially non-degenerate, then it must be tangentially non-degenerate. Okay. And then I have one question for everybody here, because I'm not so good with examples. So the question is, find Z, very smooth, irreducible, and if to be better is linearly normal, such that Z is tangentially non-degenerate, but not strongly. So we have shown that if it's strongly tangentially non-degenerate, then it's tangentially non-degenerate. Now I expect that the converse is not true, but I don't have an example. But so I hope that someone comes up with an example. It most likely some homogeneous variety give such example, but I haven't checked, and I don't know many examples. So. Okay, so now the question is, this is a sort of new notion, strongly tangentially non-degenerate. This is a new notion. So how to check something like this? So there's one lemma that, so you need to have some tool to check when an element here belongs to this guy, the sigma prime PV. So let me give you one, as an exercise of all the definitions, one lemma that the sigma is an element here, then assume all lambda. Actually, it's enough to check this for all general lambda, because if it holds for general, then it holds for every. And sigma lambda square. So here lambda perpendicular just means that vectors annihilated by lambda. Assume this is whole, this is true. Then sigma is so this is, lemma gives you how to check when a given element here belongs to sigma prime PV. This is a lemma. And if I have enough time, I'll give you proof. Otherwise, I leave it as an exercise. we have 20 minutes already. Let's see. Okay, let me give you a proof. So, proof of the lemma. So for any lambda, if lambda alpha or lambda beta equals 0, then lambda sigma alpha 0. That's the assumption. What this assumption means is this, that for any lambda, if alpha and beta is annihilated by lambda, then sigma alpha beta is also annihilated by lambda. That's the assumption. Okay. Then it's, so in other words, so this implies that any hyperplane containing alpha and beta contains sigma alpha beta. Okay. So this implies that sigma alpha beta is in the linear span of. So it's almost straightforward. So this implies that sigma is okay. So I will show you how to use this lemma, and we prove the following proposition. And dimension of Z is at least 2 if a general hyperplane section of Z is tangentially non-degenerate, then Z is strongly tangential. Okay, so this is one way to check strong tangential non-degeneracy. If its hyperplane sections are tangentially non-degenerate, then Z itself is strongly tangentially non-degenerate. Okay. And actually, this kind of thing suggests that this strong tangential non-degeneracy must be, it should be formulated in terms of vanishing of a certain cohomology, some causal cohomology. But I don't know what is the correct definition. So let's give a proof of this proposition, because this is, for me, this is the only way to show strong tangential non-degeneracy so far. So let's prove it. So suppose you are given sigma in here. So we like to show that this belongs to sigma prime of p-brid. So by lemma, we need to check sigma lambda square is in lambda for general lambda. For general linear functional, we need to check this. Then we verify this, so we prove strong tangential non-degeneracy. Now, if you take the composition of sigma and lambda, this now belongs to here. So from here already people who are very quick can guess how to prove this. But let's take composition of the sigma and lambda. Then it belongs to here. So it defines a two form. And if you restrict it to perpendicular over lambda, this is now inside here. So we need to show, to check this fact, we need to show this is 0. Okay. That's what we want to show. When you restrict it to here, you send it to here, meaning that this is 0. Now consider y is z intersect p lambda, the hyperplane section. Section of z. Then we claim that this is tangentially non-degenerate by assumption. And then we claim that this belongs to sigma y as a subvariety of this vector space. Now this is enough because by tangential non-degeneracy, this is 0. Tangential non-degeneracy. That's the definition of tangential non-degeneracy of y, that this is 0. So then by the claim, if we prove the claim, then this is 0. So we have checked everything. So it's enough to prove this claim. But this claim is equal to the following. This claim is equal to that for all alpha in y hat regular and all beta in t y hat, lambda dot sigma alpha beta is 0. This is equal to the claim. Okay, but since sigma is inside here by our original assumption, sigma alpha beta is in the linear span of alpha and beta. Because alpha is now inside, alpha is in y hat regular, but then it's inside z hat regular because you are taking general hyperplane section. And then beta is t alpha z hat. So by the assumption that this is in the linear span of alpha and beta, and then lambda dot sigma alpha beta. So let's write this a alpha plus b beta. Then this is lambda a alpha plus b beta. But alpha and beta are in lambda perpendicular, so this must be 0. So this condition is checked. So that's the end of proof. Is it okay? So this is mostly linear algebra, but combined with some elementary geometry. Okay. So now that you have this proposition, so to check strong non-degeneracy is essentially you need to check tangential non-degeneracy. So you need to know how to check tangential non-degeneracy to be able to check strongly tangentially non-degenerate. Now, tangential non-degeneracy is a more classical notion, but still there are not so many results to tell which variety is tangentially non-degenerate. So let me give you some examples of tangentially non-degenerate varieties. Examples of. So this will be used in the second lecture. Examples of tangentially non-degenerate. Varieties. How many minutes do I have now? Let's see. Okay. So let's consider the following example. So the following fact. So let's first consider this. This is more well known. Even dimensional vector space and theta is a two form, but I'll assume this is non-degenerate. Dimension of V is good. Maybe not here. Well, if the dimension of V is 1, is everything is sort of. Z is because when I take hyperplane section, if it's isolated point, then it's if it's a curve. If you take hyperplane section, then it's isolated point. It cannot be tangentially. Okay. Yeah. So it's sort of obvious. Okay, so let's consider the following situation. Because this is well known, so I'll try to start with this example. So you are considering an even dimensional vector space with two form, but then you have the notion of non-degenerate two form. So this is sometimes called the symplectic form. So let's consider this situation. You are given a symplectic form on an even dimensional vector space. Now, where is it? Okay. Now, if theta belongs to sigma z, then this means that z hat is isotropic with respect to theta. I mean, this is just terminology. People call such z as isotropic subvariety. And so this just means that theta, exactly what we defined, this is 0. That's the definition, isotropic. So under this situation, it is well known that given symplectic vector space, if you have isotropic subvariety, then its dimension is then dimension of z is at most m half. Z hat is at most half. This is well known. And if this is m, we say that z hat is Lagrangian subvariety. These are standard terminology in symplectic geometry. So as a result, we have the following proposition. So Z is in PV, and dimension V is even. And if there exists non-degenerate theta in sigma Z, then dimension of Z is less than half of dimension V minus 1. This is a consequence of what we wrote here. I just reformulated in this way. So variety inside even odd dimensional projective space. If sigma Z contains a non-degenerate element, then its dimension is less than or equal to this. Now there's a sort of generalization of this, and this was what I proved with Muk long time ago. But it's elementary, of course. This says that given any, now no restriction on dimension, and this is now assumed is smooth irreducible. If sigma Z is non-zero, then dimension of Z is less than or equal. So the same bound holds. The same bound holds as long as Z is smooth, without any assumption, as long as this is non-zero. So as long as Z is tangentially degenerate and is smooth, then its dimension cannot be bigger than this. A small, bigger than this. So if Z has a sufficiently small codimension, then it's always tangentially non-degenerate. That's the statement. And this proof is essentially this plus Jacques' theorem on tangency. So combining these two, you can generalize this to this form. So any subvariety of small codimension, small meaning bigger than half of the ambient dimension, that is tangentially non-degenerate if it's smooth. That's the proposition. So this means that many smooth variety are tangentially non-degenerate. Okay, now I'll state the following thorough. This is something I proved recently, so it's new, but it's still rather elementary. This is okay. This is smooth, linearly non-degenerate. Complete intersection. Of dimension, a positive dimension. Is tangentially non-degenerate. So this implies that if dimension is at least 2, then strongly tangentially non-degenerate. By our proposition, because if you take hyperplane section of smooth complete intersection, then the hyperplane section itself is smooth complete intersection. So as long as it has dimension at least 1, it is tangentially non-degenerate. So if it has dimension at least 2, then it's strongly tangentially non-degenerate. So that's the theory. Now what's the idea of the proof? So to prove this, I need some definition. But I'm sure that people in more like CGGs working on CGGs must have more standard proof of this. But the proof I give is something I cooked up. So the argument I give should be able to be, one should be able to translate it into some causal language. But let me give a very geometric way of doing it. So I will define the following. The definition. So when we are given, now I will assume this is smooth variety. Then we have the normal bundle. This is conormal bundle of G. Okay. And the normal bundle, NG is normal bundle. Has a fiber. So let's just recall this. What was the fiber of normal bundle? At a point, the fiber of normal bundle is just homomorphism from U hat to V. The quotient bundle. That's the quotient space. This is the fiber of normal bundle. And then we define H0, P, V, I, Z2. These are quadratic forms vanishing on Z. In other words, this is Q in what's that? Q Z Z for 0 for all Z. Yeah, this is just the standard definition. All quadratic polynomials vanishing on the variety Z. Now I define the following homomorphism, chi. And this must be one of the standard homomorphism. But let's recall what this is. So this is defined as follows. So suppose you are given a quadratic form here, which vanishes on Z. Then chi Q is now an element here. So to specify an element here, I have to evaluate it here where phi is now NZU and U is in G hat. So I have to specify what's the value of this at this point. Because this is a section of this conormal bundle, which means it's a functional on the normal bundle. So I will define this as QU phi U tilde, where phi U tilde in V represents phi U inside V. Okay, and so phi is inside here. This is home of so given an element here and element of the tautological element at that point, square, because this is square, I will define this functional on here in this way. That's how this homomorphism is defined. I mean, this is one of the standard homomorphism, I think, coming from some general exact sequence. But this is the precise meaning of this homomorphism. And here, this definition is independent of choice of phi u. So this is an element representing this, but you can choose many different such elements modulo here. But this definition is independent of this choice because by definition q u t u z hat equals 0. Because of this. Because q z z equals 0 by derivative, taking derivative. Maybe it's better to write u here, but yeah, if you take derivative of this, then you see that this is 0. So this definition is independent of choice of this representative. So that defines this homomorphism. Now, here's the proposition. So, this is smooth, linearly non-degenerate. Then, chi is injective. So, this homomorphism is injective. And that's sort of easy. And 2, if chi is surjective, then z is tangentially. Now I remember one thing. Okay, so this is the proposition. Now this is remark for those who want to look at this more. It's not directly related to this, but the remark is that tangential non-degeneracy, tangential non-degeneracy, is I think it's something what people related to what people call injectivity of Weyl-map. There's some homomorphism coming from smooth variety, Gauss Weyl-map, and this notion is related to injectivity of Weyl-map. So I mean, these things maybe can be translated into the language of Weyl-map, but since this itself is not well known, so let me do it. This is more elementary. Okay. So that's the proposition. This homomorphism is always injective, and if it's surjective, then it's tangentially non-degenerate. And so first of all, this proposition implies theorem. Why? Because if Z is a complete intersection of type, say M1, M2, MK, these are the multi-degree, and then we know that the normal bundle of Z is isomorphic to the direct sum of OMI. And since it's linearly non-degenerate, these are all at least 2. So the normal bundle splits into line bundle, and then H0 of PV IZ2 is isomorphic to H0 of Z. So because this means quadratic polynomials vanishing on Z, and that's exactly given by quadratic terms here, the degree 2 terms here. And if you take conormal bundle and twist by 2, then this is exactly those MIs which has value 2. So both of them are exactly given by O2s here. So they are isomorphic. So chi is isomorphic. So by proposition, Z is tangentially non-degenerate. So this proposition implies the theorem. Now to prove the theorem, I will skip the injectivity. It's easy, and injectivity is something which has no geometry. I mean, it's always true. It comes from linear non-degeneracy. Doesn't use any geometry. So let's prove the surjectivity. Proof of 2. Surjectivity implies tangential non-degeneracy. So let's do this. So suppose theta is in sigma z, and we want to show it is 0. So in other words, this means that theta alpha is 0 if alpha is z hat. Yeah. That's the definition. And theta is a true form with this property. Now I will define the given such theta. And we want to show that this theta is 0. That's what we want to show. If this is true, then theta is 0. That's what we want to show. So let's recall that this is theta is just two form satisfying this, and we want to show it's 0. So now we define theta prime. A section of this appearing inside chi, or where chi was this, H0. Okay, we define theta prime as follows. Almost the same definition as what appears in chi. So theta prime p tensor where, in the same way as before, that where phi is inside nzu and phi u tilde represents represents phi u in V modulo T. Okay, so we define an element here associated with theta in this way, and this definition is good, independent of choice of phi u tilde because of this. Because of this. Because this is 0, it's independent. You can already choose it. So now, since chi is surjective, there exists Q such that chi Q equals theta prime. So theta prime is an element here, and the chi is surjective, so there must be a quadratic form with this property. So in other words, Q alpha phi alpha theta equals theta alpha phi for O alpha. So this is true. But then you can reach any vector as an element of the normal vector. So this implies that Q alpha V, V is theta alpha V for all V in V. Because Z is linearly non-degenerate, so any vector can be represented, can represent a normal vector of the variety. So this is true. But then this is a contradiction, because this means that Q alpha beta is theta alpha beta for all alpha beta by linear non-degeneracy of Z. But this is symmetric, and this is anti-symmetric. This is contradiction. So this means that they must be 0. It must be 0, identically. So this means theta is 0. So that shows tangential non-degeneracy. Almost time. So all these are completely elementary, but I think there's something people interested in projective geometry and CGGs may try to translate this into CGGs and formulate more general notion. So for example, I think I defined something about whom this and then this. But this must belong to in the sequence of some other objects. So there may be something involving triple wedge product. So I don't know what is exactly going on. So there must be some general picture where this is just a special part of this general vanishing theory. Anyway, so in the afternoon I will now go to more global geometry and why these are interesting to me. Thank you.